Hello students, in this video you are going to learn about electronic configuration of different species like dioxygen, dioxygen cation, dioxygen anion, dioxygen dianion, dinitrogen molecule, dinitrogen cation and dinitrogen anion. I would like to emphasize the distinct difference between these two molecules and ions. On the left you see that the 2pz, if you look at the molecular orbitals of this section and this section corresponds to for example boron, diboron, dicarbon, dinitrogen. All these molecules follows this type of diagram, that is molecular orbital diagram, whereas dioxygen, difluorine and dineon follows this molecular orbital diagram. Let me clearly explain what is the difference between diboron, dicarbon, dinitrogen and dioxygen. Let me clearly explain the distinct difference between diboron, dicarbon, dinitrogen, dioxygen, difluorine, dineon. Okay, if you look at the 1s orbital, is exactly the same. There is no change in 1s orbitals. Both molecular orbitals and atomic orbitals are very simple. Similarly, for 2s orbital, for both the oxygen type molecular orbital and nitrogen type molecular orbital same. Therefore, 1s orbital of dinitrogen and dioxygen are same. 2s orbital molecular orbitals for dinitrogen and dioxygen are same. The key difference is the placement of or the energy of sigma 2p z. In the case of dinitrogen, sigma 2p z placed little bit higher energy than pi 2px and pi 2py, whereas in the dioxygen case, the 2pz orbital occupies the lower energy. This is the only difference between oxygen, nitrogen type and oxygen type. I clearly explained. Look at the 2pz orbital, that is bonding level, because look at the anti-bonding level in this both diagram is exactly the same. Only change is sigma 2pz placed above the 2px pi 2px pi 2y in the case of dinitrogen and dicarbon diboron, whereas the sigma 2pz occupies the lower energy as compared to pi 2px and pi 2y. There is a only difference in these two cases. So look at the ionic species and the molecule species given. Okay, since the bond order calculation is mainly bond order as well as electronic configuration is mainly depend on the arrangement of electrons in the molecular orbital O2 case. In this we have a 16 electron because each oxygen has 8 electron, therefore totally 16 electron. How we can fill the 16 electron in this molecular orbital? Very simple. In this side, for example, let me write the electronic configuration of oxygen: 1s2, 2s2, 2p4. This is the one of the oxygens. Here also 1s2, 2s2, 2p4. Another oxygen. These are atomic orbitals of oxygen. These are atomic orbitals of oxygen. The middle part is molecular orbitals. The lower energy orbitals are called bonding molecular orbital and higher energy molecular orbital called anti-bonding molecular orbitals. Okay, so let's fill the electrons. 1s2, 1s2 electron, 1s2, 2 electron, again 2s2, 2 electron, 2s2, 2 electrons. Next fill the 4 electron in this 3 orbital. This is 2px, 2py, 2pz. So 1, 2, 3 and 4. Similarly 1, 2, 3 and 4. So all the atomic orbitals are filled according to the given electronic configuration. Now fill the molecular orbital, bonding molecular orbital as well as anti-bonding molecular orbital. So totally 4 electrons, 2 electrons occupies the sigma 1s and another 2 electrons occupies sigma star 1s, that is anti-bonding molecular orbital. Similarly 2 electrons occupies sigma 2az and 2 electrons occupies anti-bonding molecular orbital level, that is sigma star 2p sigma star 2s. Now look at here, this 2p orbital has 4 electrons and this 2p orbitals has 4 electrons, therefore total 8 electrons. Now fill the 8 electrons in the increasing order of energy. Here in this case, this dinitrogen, dicarbon, dinitrogen, diboron case, the 2px, 2py occupies lower energy position as compared to 2pz, that means sigma 2pz, whereas in the oxygen, difluorine and dineon case, the 2pz occupies lower energy position compared to pi 2px and pi 2py. So therefore first 2 electrons filled in the 2pz, that means sigma 2pz orbital. The next 2 electrons fill in the following orbitals, 2px, pi 2px and pi 2py. We have another 2 electrons left, so therefore it can occupy pi star 2px and pi star 2py. So all total 8 electrons are filled in the molecular orbitals like 2, 4, 6 and 8. That's it. So filling of orbitals is very similar to the case of dinitrogen. Okay. So I hope you understand how molecules are formed based on linear combination of atomic orbitals and how molecular orbitals are placed in the depending on their energy level. This is very important in terms of electronic configuration and bond order calculation. So let me summarize one more time in order to understand. So these 2 types of molecular orbital diagrams were represented for diboron, dicarbon, dinitrogen case, whereas that means the second section or the second diagram represent dioxygen, difluorine, dineon case. The only difference is the placement of sigma 2pz. This sigma 2pz and difluorine, dineon cases, that sigma 2pz occupies lower energy level compared to pi 2px and pi 2p. This is the only key difference between these 2 types of molecular orbital. So now let's write, even if you want to fill, for example here, initially in the last video we have filled with dinitrogen. Let me fill for dicarbon. So dicarbon means what? Dicarbon 1s2, 2s2, 2p1, sorry 2p2. Here also 1s2, 2s2, 2p1 for dicarbon. Okay, so 2 electrons, 1s2 to 1s2 fills as 1s orbital, similarly 2s orbital. This is common for most of the cases. Here we have a 1 electron in this level and 2 electron in this level and 2 electron in this, totally 4 electron. So 4 electron completed. Okay, look at the molecular orbitals. We don't see any unpaired electron, therefore this is called dicarbon. That is dicarbon is a diamagnet. Whereas in the case of dioxygen, this molecular orbital paired. But look at the unpaired electron present in the pi star 2px and pi star 2py. 2 unpaired electron present. Therefore dioxygen is an example of paramagnetic. Let me write the electronic configurations generally. So listen carefully students, the distinct difference is the placement of sigma 2pz in the case of dioxygen, difluorine. Why this actually occurs? Because here 2s 2p orbitals are mixing, here they without mixing. Okay, that doesn't require now, just understand the placement of 2p sigma 2pz, because this is the key difference between the nitrogen type and oxygen type molecular orbital diagram. Let's write the corresponding electronic configuration. Look at this. First dioxygen, we have sigma 1s. So sigma 1s has 2 electrons. Similarly sigma star 1s has 2 electrons. Next sigma 2s has 2 electron. Next sigma star has 2 electron. Sigma star 2s are 2 electron. Look at the 2p sigma 2pz. Sigma 2pz has 2 electron. Look at the pi 2px and pi 2py. This is bonding molecular orbitals. So each these orbital occupying a same energy level position. Therefore you have to represent with a equal symbol. So pi 2px 2 electron equals to pi 2py. Then we have 1 electron in the pi star 2px level and 1 electron in pi star 2py level. Therefore, pi star 2px 1 equals to pi star 2py 1 electron. So this is the electronic configuration of dias. For example, in the case of carbon, let me sigma 1s has 2 electrons and sigma star 1s has 2 electron, sigma 2s has 2 electron, sigma star 2s has 2 electron. Here pi 2px has 2 electron equals to pi 2py 2 electron. Look at the equal symbol representing that these two molecular orbitals are in the same energy level. That is the meaning of the equal symbol. Hope you understand. And so this is a electronic configuration for O2 O2. In order to O2 plus 1 electron must be removed. You can remove either one of these orbital. I can remove 2py. Let's write the electronic configuration of the given species dioxygen. Sigma 1s 2 electron, sigma star 1s has 2 electron, sigma 2s has 2 electron, sigma star 2s has 2 electron, sigma 2pz actually 2 electron, pi 2px 2 electron equals to pi 2py 2 electrons. Let's count the number of electrons because that should be 16. 2 plus 2, 4, 6, 8, 10, 12, 14 and pi star 2px 1 and pi star 2py 1. So totally 16 electrons. Similarly for O2 plus. In this case all the orbitals are same except this. Let me write sigma 1s 2 electron, sigma star 1s has 2 electron, sigma 2s has 2 electron, sigma star 2s has 2 electron, sigma 2pz 2 electron, pi 2px 2 electron equals to pi 2py has 2 electron. Here pi star 2px 1 electron. That's it. No electron because this electron is removed. This is a 15 electron species. This is 16 electron species. Okay. Next O2 minus. So O2 minus. Similarly, sigma 1s has 2 electron. Sigma star 1s has 2 electron. Sigma 2s has 2 electron, sigma star 2s has 2 electron, sigma 2pz has 2 electron, pi 2px has 2 electron equals to pi 2py has 2 electron and pi star 2px 2 electron equals to pi 2py pi star 2py 1 electron. Let's count number of electrons. 2, 4, 6, 8, 10, 12, 14. 17. This is 17 electron species. This is 17 electron species. 2, 4, 6, 8, 10, 12, 14, 16 and 17. Next 18 electron species. O2 2 minus. This is 18 electron species. Sigma 1s 2 electron, sigma star 1s 2 electron, sigma 2s 2 electrons, sigma star 2s 2 electron, sigma 2pz 2 electron, pi 2px 2 electron, pi 2py 2 electron, pi star 2px 2 electron, pi star 2py 2 electron. Therefore, this is an 18 electron species. So, oxygen, dioxygen molecule 60 electron species, oxygen cation is here. The oxygen plus oxygen cation is 15 electron species, 17 electron species, and 18 electron species. Depending upon the number of electrons, the molecular orbitals are filled. For a comparative reason, let me give for dinitrogen. In dinitrogen case, sigma 1s has 2 electron, sigma 1s star 1s has 2 electron, sigma 2s 2 electron, sigma 2s sigma star 2s 2 electron. Here is the twist. In this case, for dinitrogen, first 2px 2py comes, then only sigma 2pz comes. That is the difference. So this is a 14 electron species. Already we filled with 8 electrons. Let's fill with the 2px 2 electrons equal to 2p pi 2p pi 2p y 2 electrons. Let's count 2, 4, 6, 8, 10, 12. Then we have a sigma 2p z 2 electron. Look at this. In the case of oxygen, sigma 2p z comes before the pi 2px and pi 2py, whereas in the nitrogen case, sigma 2p z comes after the pi 2px and pi 2py. This is a key difference. I hope now how you can write the electronic configuration. Let's count let's calculate the bond order and fix or compare the stability of the given species. So bond order equal to NB minus NA by 2. So NB represents bonding level molecular orbital electrons, which is 2, 4, 6, 10. So 2, 4, 6, 10. So in the bonding molecular orbital, we have a 10 electron minus antibonding level. This is antibonding level, this is antibonding level, this is antibonding level. So 2, 4, 6, which is 2. So double bond exists between oxygen. Can we calculate for O2 minus bond order? O2 minus. In this case, let me write the electronic configuration. O2 minus. Sigma 1s has 2 electron. Sigma star 1s has 2 electron. Sigma 2s has 2 electron. Sigma star 2s has 2 electron. Sigma 2pz has 2 electron. Here pi 2px has 2 electron equals to pi 2py has 2 electron each. In this case, this is an 18 electron species. So one electron must be added in these two orbitals. Therefore, it becomes pi star 2p x2 equals to pi star 2p y2. Now underline the bonding level molecular orbitals. This is a bonding level molecular orbital. This is a bonding level molecular orbital. This is a bonding level, and this is a bonding level. Now count the number of electrons here: 2, 4, 6, 8, 10. So NB equal to 10. Na count Na, that is antibonding level, antibonding level, antibonding level. So 2, 4, 6, 8. So Na equal to 8. Formula bond order equals to 10 minus 8 by 2, roughly equal to 1. So the value of bond order for O2 minus is 1. Similarly, can we calculate for O2 plus? O2 plus. Let's write electronic configuration. So bond order for The dioxygen is bond order for dioxygen is 2, bond order for O2 minus is 1. Let's calculate for O2 plus. Sigma 1s 2 electron, sigma star 1s 2 electron, sigma 2s 2 electron, sigma 2s sigma star 2s 2 electron, sigma 2pz 2 electron, pi 2px 2 electron equals to pi 2py 2 electron. Here this is a 15 electron species. Therefore we already completed with 2, 4, 6, 8, 10, 12, 14. So only one is left, that is pi star 2p x1. That's it. Now underline the molecular orbitals, sorry, that bonding molecular orbital, bonding level. So NB now equals to 10, that is 2, 4, 6, 8, 10. NA equals to 2, 4 and 5. So the bond order equals to 10 minus 5 by 2, which is 2.5. So the bond order in this case is 2.5. So we know that the stability of the given species is based on the bond order. The stability of the given species based on the bond order. So the bond order for this species is highest as we calculated. Therefore, this is the highest stable. When the bond order is larger, that means the bond order value is higher, the higher the stability is. Like this only the stability of the compound or given species. It could be either neutral molecule or cation or anion. That doesn't matter. We have to calculate the bond order. Based on the bond order only, we can fix the stability. Therefore, this highest stability, and then the bond order is this is the next second highest stability, and followed by this and this. So hope you understand the concept behind the bond order and the stability calculations. Thank you very much.